So we've been talking about the work done by a constant force. Now, what if we have a force that is changing with time? So, for example, this is an example right here where if you look at this graph, as you move the object from point A to point B, the force is not constant, but the force is actually changing. So because the force is changing, it means that I cannot just calculate the work by taking the product of the force times the distance. But in this case, we need to use calculus. So if this is my force and this is my displacement, and if this is the graph of the force, then I can calculate the work by calculating the area under this graph right here. So in mathematics, we can write this equation as an integral. So generally, we can write this as an integral. So the work done is just the integral of the force times dx from x initial to x final. So again, this is the main equation that we have right here. So work done is the integral from xi to x final, fx dx. Now fx here is just the force that is pointing in the x direction. All right. So now let's look at this example right here. So in this example, we're going to calculate the work done by the force that is given by this on this picture. So we have a force that is going to move an object from this point to this point right here. So the total displacement is 6.0 meters. But notice that the force is not constant, the force is changing. So if I want to calculate the work done, the first thing that I'm going to do is that I can calculate the work from point A to point B. So from point A to point B, the force is just 5.0 newtons and the displacement is 4.0 meters. And so I can just multiply that together to get my 20.0 meters. Now when I go from point B to point C, the force is changing, it's reducing. So I need to calculate this area. And because this area is a triangle, then I can calculate the area of this triangle by doing half times the base times the height. So if you do that, you get 5.0 joules. Now we can calculate the total work from point A to point C as the sum of the work from point A to point B plus the sum of the work from point B to point C. So if you do the math, you end up with 25 joules. All right. So now we're going to take all of this and apply it to one example right here, which is the work done by a spring. So in this example here, the first thing that we're going to look at is a spring. So in this spring right here, so when x is equals to 0, the force on the spring is just equals to 0. So this is the equilibrium point. When x is positive, it means that the spring has been stretched. And when x is negative, it means that the spring has been compressed. So notice that when the spring is stretched, the force on the spring is acting to the left. And when the spring is compressed, the force on the spring is acting on the right. So the point is that the force on the spring is always acting in the opposite direction as the displacement of the mass. So generally, because the force of the spring is always acting in the opposite direction of the displacement, we can write the force of the spring using this equation right here. So the K value here is called the spring constant, or maybe it's also called the force constant. And it's a quantity that I'm going to talk about just in a little bit. I'll tell you exactly how we can calculate this K value. So in terms of the vector representation, we can write the force of the spring in this form right here. All right. So now, if we want to calculate the amount of work, so suppose that we start from some initial position right here, and then you want to stretch it from this point to this point right here. So you want to calculate the total work done in moving this mass from this point to this point. So because the force is changing as you go from this point to this point, we need to calculate the work using an integral. So if you do this integral, so you integrate from negative x max to 0, you get 1/2 kx squared. So this is the amount of energy that is converted into the kinetic energy of this mass right here. All right. Okay, so if we make a graph of the force of the spring as a function of x, the graph is going to look something like that. So again, we can calculate the work done by the spring on the block as it moves from negative x max to 0. So if you just calculate this area right here, then we can get the same equation. So this is a triangle, and so that area is 1/2 kx squared, x max squared. So we can also do that by using an integral. So generally for any displacement, for example, if you're going to go from x final to x initial, then we can calculate the work by using this equation. So you just integrate from x initial to x final to get this equation right there. All right. Now, this is also the same example right here. So if you just use calculus and we integrate the applied force from x initial to x final. So in this case, my x initial is negative x max and my x final is 0. So you get negative 1/2 k x max squared. All right. Okay, I'm going to let you guys also look at this quiz number 7.4. Okay, now let's look at this example right here, example number 7.5. So in this example, I want to talk how we can calculate the K value. So the K value is called the spring constant, or maybe it's also called the elastic constant. So these two pictures try to explain exactly what is going on. So the first picture here is a spring. There is no mass on it. The second picture is a spring that has been compressed, that has been stretched by a distance d when a mass is added to it. So let's assume that the stretch is given by 2.0 centimeters. So a stretch of 2.0 centimeters is produced on the string whenever a mass of 0.55 kilograms is placed on it. So if you want to calculate the K value, what we're going to do is that you just say that the force of the spring minus the force of gravity has to be equal to 0 when the system is at rest. So this is just saying that the sum of all the forces must balance. So from here you get the force of the spring is equal to m times g. But because the force of the spring is equal to k times d, so solving that equation you can get k equals to m times g over d. And so if you substitute, you get 2.7 times 10 to the 2, and this will be in Newton per meters. Now, if you want to calculate how much amount of work is done by the spring on the object as it stretches through this distance, so generally because you start from the point where the initial displacement was 0, so that initial energy is just equals to 0, and the final energy is 1/2 k times d squared. And so if you plug in that value, you get negative 5.4 times 10 to the negative 2. So notice that the energy here is negative. So the negative value simply means here that so what you're doing is that you're stretching the spring. So when you stretch the spring, the work is negative. When you compress the spring, the work is positive. So we can also we could have calculated the work done also using this equation right here. So if you want to calculate the work done by gravity, you can just take mass times gravity times this distance, and then if you substitute that value, it gives you 1.1 times 10 to the negative 1 joules.